So if we take a 1,3-dicarbonyl and remove a hydrogen, we're always going to remove the same hydrogen. It's always going to be the hydrogen between the two carbonyls. And so now we're going to look at how do we use that enolate that we can make, and how do we use that in synthesis? What kinds of things can we make from that enolate? So again, we're going to start with 1,3-dicarbonyl. This time I'm going to make one of those carbonyls an ester. And whatever, we can put anything we want over here. I'm going to put a cyclohexyl group just because I like drawing hexagons. Okay. So now we're going to make the enolate here. Again, we want to match our base with the ester group that we have here, right? And so I'm going to use a base that is OCH3 minus to match the ester group here. When we make enolates of esters, when making enolates from esters, use the alkoxide base, right? So the negatively charged oxygen that matches the ester group. Right? What this does is it prevents us from doing substitution, right? So if the OCH3 minus that we're using as our base, so this OCH3 minus up here, acts as a nucleophile and does carbonyl substitution, like a waterfall reaction, at this 1,3-dicarbonyl, right? Notice that the OCH3 would just replace an OCH3 and we get the same starting material back. If we use a different base, OH minus or something else like that, if we use OH minus, for example, if we take OH minus and add it to this, we will replace the OCH3 with OH, and then we've got a carboxylic acid and we've changed our overall reactivity, right? And that's not what we want. What we want to do is make an enolate. So of course we're going to do that first, right? So the first thing we're going to do is make the enolate. We know that we're going to remove the hydrogen from the position between the two carbonyls. Even though this is a tertiary position over here, this is not the most acidic position because we have additional resonance, because we have two carbonyls here. So because we have a 1,3-dicarbonyl, we're only going to remove the hydrogen from between those two carbonyls. And we get this enolate. Now this enolate is going to, now we can do basically anything that we did with our previous enolates, we can do with this enolate, right? We can do things like aldol reactions, we can do SN2 reactions, we can do Claisen reactions, we can do Michael additions, right? All of those things are possible. We have a nice enolate here. Enolates do what enolates do. I'm just going to do an SN2 reaction because what the heck? That's the one that I've chosen. Bromine acts as a leaving group. This thing gets kicked off and we've added our 7 carbons, right? So again, we always want to make sure we count our carbons and make sure we got everything accurate for our carbons there. And notice that this enolate reacts the same way that all the enolates that we've used so far react. That alpha position is the nucleophile. We add that alpha position to whatever we're adding in, right? In this case, the SN2 substrate. The alpha position is the thing that ends up connected to this carbon here. We reform the carbonyl, the alpha carbon acts as a nucleophile, that adds in and we get this, right? We've added 7 carbons down here, but the starting material more or less remains the same, except for a new bond at the alpha position. Okay, so far, this is just an enolate reaction. I've shown you enolate reactions doing SN2 reactions before. You're probably thinking, what? Why is this important, right? And what this does is this allows us to now, we can control where the enolate shows up because it always shows up between these two carbonyls, and we can remove this carbonyl, this ester group, using a reaction that we've seen before, but maybe haven't thought about in a while, right? And so the other thing that these types of 1,3-dicarbonyl groups do is they allow us to remove this ester. Ester can be removed by decarboxylation. All right, so now you're scanning back through your notes, thinking back to all the unforgettable videos that you've seen in this class, trying to remember what decarboxylation is. Decarboxylation is when, quick review of decarboxylation. Decarboxylation happens when you have a 1,3-dicarbonyl compound, and one of those carbonyls is a carboxylic acid. Right? If you heat this up, and you can have whatever you want here, right? These R groups can be anything. So you can have anything you want over here as long as you have carbonyl, carbon, carboxylic acid. When you heat these up, you lose CO2, right? And you get out basically this compound where this carboxylic acid gets lost. The mechanism for this, if we were to draw it out, although I will not ask you to do this, right? The mechanism for this ends up looking like this. If we rotate that carboxylic acid around, we move those arrows in that direction, we end up with the enol and then that enol, if we just transfer the H plus to the carbon from the oxygen, that enol is the same as the ketone. So again, the mechanism is not something you need to know. What's important is that you start with a 1,3-dicarbonyl with a carboxylic acid, and then you heat it up to lose CO2, right? So if we already have the 1,3-dicarbonyl in place here, we just need to convert this ester to a carboxylic acid, and then we can get rid of this. So how do we convert an ester to a carboxylic acid? I'm hitting all the highlights from a month ago in this video, right? We can use H plus H2O, or you can use sodium hydroxide, right? So either one, basically you just need to add water in a nucleophilic, to do a nucleophilic substitution at that carbonyl. I usually prefer to use H plus H2O just because if you use sodium hydroxide, there is an enolate possibility here. And if you use base, you could potentially make the enolate. So I'll almost always use H plus H2O, but you can definitely use sodium hydroxide and it would probably work just fine. So H plus H2O will make the carboxylic acid. And then we heat it up, lose CO2, and we get this compound. Right? So notice we've lost this carbon over here, but all the other carbons are in place. So we have two 6-membered rings, and then we have 1, 2, 3 carbons in between them. We have two 6-membered rings. We have 1, 2, 3 carbons in between them. We have a carbonyl at carbon 1 and a benzene ring attached to carbon 3. So we get this compound. All right. So this pattern of taking a 1,3-dicarbonyl compound, I'm going to give you kind of the generic run through here. You take a 1,3-dicarbonyl compound, make the enolate, react the enolate, right? So add something to the alpha position. Alpha position adds to something, right? And there are a lot of things that we can have the alpha position add to. We've gone through a whole bunch of reactions, the aldol, the Claisen, the Michael, the SN2, the bromination, right? The alpha position can add to a lot of things. It adds to something to make a new compound. Then we convert to the carboxylic acid. And decarboxylate. Right? Loss of CO2. This is a really common way to make a bunch of organic compounds. Right? And what this does is the 1,3-dicarbonyl is powerful because we only ever make the enolate in one place. And so if we have a situation where we can't really decide, let's say you have 2 secondary carbons, right? And you want to make the enolate at one of those secondary carbons and not the other. we can't use kinetic and thermodynamic to differentiate between those two because they're equally substituted. But if you have a 1,3-dicarbonyl compound, you will always make the enolate at the position between those two carbonyls. And so if you make a compound that has a 1,3-dicarbonyl in it, then you know exactly where your enolate can form, and you can start to make things that you may not be able to make using just standard basic um, enolate chemistry. And so this kind of pattern and process is really common. You'll use it a lot. The problem set number 6 is all just using these types of reactions, right? Start with a 1,3-dicarbonyl, go through this process to make the thing that you want, and then sometimes you'll have additional things to do once you finish this process. But in general, this kind of sequence is something that you're going to see a lot of. So hopefully there will be some practice on that. The problem set will kind of reinforce these ideas, and I hope that you enjoy all of that.